Hi, and welcome to Module 10 of Lecture 2. In the last module, we stopped with these formula, which we used to calculate the coefficients and the constant in a simple bivariate regression, an ordinary least squared regression, looking at the relationship between an x and a y. Now, an independent variable and a dependent variable. What we didn't talk about too much was the uncertainty inherent in those estimates, so we're going to do that now. Because we're basing these estimates on a sample from the whole population, we're going to be uncertain about the actual true values of alpha and beta. Note, we are assuming there's an underlying true model of the world in which the dependent variable y equals alpha plus beta times the independent variable x. That is assumed to be true. The uncertainty we're talking about here is not uncertainty in whether or not that's actually true. For any kind of statistical analysis, you always assume, in general, you almost always assume that the model that you're working with is a true model. It's a true data generating process, if you remember from an earlier module. It's a true way in which data were generated. Therefore, our uncertainty here is in the degree to which we accurately measured those population parameters, alpha and beta, by using our sample from the population. As before, our uncertainty is going to get reduced the larger the sample is. If we had the whole population, we shouldn't have any uncertainty at all about our estimates because we actually measured the true values of alpha and beta in the population. We're going to call our measure of uncertainty, as usual, the standard error. And there's going to be a standard error for alpha and a standard error for beta. And the smaller all the standard errors, the more confident we are going to be that our estimates of alpha and beta are going to be accurately represent the true values in the population. Okay. Now, we might care about in general the uncertainty around alpha, but we often don't care about that as much. And the reason is alpha doesn't relate directly to our hypotheses. Our hypotheses are in general that some change in x leads to a change in y. Whether or not alpha is 7 or 412 doesn't really change the relationship between x and y, between a change in x and a change in y. If I look at the change in y divided by the change in x, that's the slope of the line. The intercept is unaffected by the slope of the line. Right? You can have an intercept like this or like this with the same exact slope. And since the slope is representing the degree to which y changes with x, and since that's our hypothesis in general, we generally care a lot about beta and its uncertainty, but not as much about alpha and its uncertainty. All that said, alpha is really important for prediction, which we'll talk about at the end of this module. If you're trying to predict values of y from values in x, then alpha is essential because the intercept changes the prediction from down here, for instance, to up here. That's a big difference. So alpha is really important for prediction, but not as much for hypothesis testing. And because political science has traditionally not spent so much time with prediction, although it's changing a lot now, and a lot of time with hypothesis testing, we tend to focus on beta and its uncertainty and not alpha and its uncertainty. So because our goal, again, is to determine if our independent variables affects the dependent variable, and that's related to uncertainty around beta, which we're going to talk about now. So remember our example from last module. We have a line, a best fit line, which minimizes the sum of squared deviations, the sum of squared errors around the line, and we calculated an alpha hat and a beta hat. Typically, if you run this through a piece of statistical software like R or Stata or whatever you happen to be using, you'll see it pop out. If you run regression, you'll see the output in a tabular form in a table, and there'll be at least 2 columns. The coefficient you estimate for your variable, and the standard error on that coefficient. Here, variable is either the independent variable explicitly, in which case the SAT was your independent variable, or your constant, you might think of alpha as multiplying a 1. So the constant here is the variable of 1. It's the constant variable. So here it's saying your coefficient on that constant, on that 1, is alpha hat, which is negative 0.57, with a standard error of 0.78. And the coefficient on the SATs is 0.0031 with a standard error of 0.0007. So this is usually the output. Sometimes you get additional columns that do some of these things for you. We're not going to show them here because we're trying to do them ourselves. So now what we need to do is figure out whether or not that coefficient on the CTs has statistical significance, whether or not we believe it is meaningfully different from 0. Remember, just like before with simple bivariate correlations, this isn't much different. And in fact, as we saw last time, the equation for the coefficient, I'll put a few slides up here, contains the covariance between x and y, which is the same thing that the numerator in a bivariate correlation coefficient does. So as in both cases, we're trying to see if the correlation between x and y is 0 or statistically significantly different from 0. 0 being our null hypothesis of no correlation, and non-zero being our research hypothesis. So that's what we're trying to do here. And it turns out we're going to do it in much the same way we did before. We're going to form a hypothesis test from our coefficient on x in the same way we did before. For the chi-squared test we did before, we compared the observed table we saw to a table we would have expected to have seen had there been no relationship. Similarly, we're going to compare our observed beta to the value of beta we would have expected to have seen if there had been no relationship. In the difference in means test, we did a t-test, which we compared two values and divided the difference by the standard error. Here, we're going to again do a t-test, and we're going to compare two values, in which case 1 is 0, but we're going to compare two values and divide the difference by the standard error. So it's very similar to what we did before in multiple ways. And in fact, it's easier because the second value we're going to calculate is going to be 0 with no error. So the overall formula is going to be much easier than the difference of means formula. Okay, so once again, we're going to try to reject the null hypothesis. If we have a non-directional hypothesis, we just say x and y are related in some fashion. As you change x, y changes. Then the null is that there's no change, they're unrelated. So the null hypothesis is that beta equals 0. So the null here is that as you increase x, as you change x, you get no change in y. We're going to use what's called a two-tailed test to check to see if the coefficient is significantly different from 0 in either direction. A two-tailed test means, think back to the normal distribution and the bell curve and all those pictures we saw with the 68% and the 95% and the 99% area under the curve. And the idea of all that hypothesis testing was, if the null is true, then the coefficient should be at the mean of that normal distribution at 0. The further out the measured coefficient is from 0, the less likely it occurred in a given sample, given the true mean was 0. If the true mean is 0 and you get a beta of about 0.5 standard deviations from 0, that's quite likely to have happened by random chance. Therefore, you don't reject the null hypothesis that the true coefficient is 0. As you get a coefficient that goes further and further away from 0, it becomes less likely to have been attained by chance in a particular sample, and we become more likely to reject the null hypothesis. The p-value we calculated before was the chance that that the null is true here, right? Given how far away you got a value of the test statistic. So in this case, our test statistic, in a sense, is our what's going to be beta divided by the standard error, our estimate of beta divided by the standard error. But the further away that is from the mean, the less likely it occurred by chance in a reality in which the truth was that the mean of the distribution of our test statistic was 0. Let me say that again because it's important. The assumption of a null hypothesis is that the actual true population value of beta, of a coefficient on x, is precisely 0. Then we take a sample and we calculate a regression coefficients from that sample. We get some value beta hat. If beta hat is close to 0, if beta hat divided by a standard error is close enough to 0, we can't say that didn't happen just by chance. So we don't reject the null hypothesis. The further beta hat over the standard error gets away from 0, the less likely it happened by random chance in a world in which the truth was that beta equals 0. If you go out far enough, plus or minus 2 standard deviations away from 0 in a normal distribution, the chance that you actually obtain that particular value for your sample of beta hat, given the truth was that beta equals 0, is going to be under 5%. At that point, we say we are 95% confident that we can reject the null hypothesis. We call it a two-tailed test if we don't know what direction we're looking in. And we're going to look both, there's a half chance it could be to the right, to your left, I guess my right is flipped. There's a half chance it's on the positive end and a half chance on the negative end. So we're trying to show a 5% chance of getting it wrong, of a type 1 error. Then we split that 5% into 2.5% on one side and 2.5% on the other side. And that's what we saw with the plus or minus 1.96 critical values on a normal distribution. If the statistic you calculated ends up further out than 1.96 or negative 1.96, we say reject the null hypothesis that the truth is 0. That's a two-tailed test because it could be either far away from 0 in one direction or the other direction, and we don't know in advance. So we split up the 5% to 2.5% on each side, and we calculate it that way. A directional hypothesis is that the null is that we believe, say, as you increase x, y increases, or as you increase x, y decreases. The first one posits a positive correlation. The second one posits a negative correlation. A positive effect and a negative effect of x on y. So, if we believe strongly that there's a definite direction to our effect, then our null takes a little different form. Instead of saying that as I increase x, as I increase my test statistic, in either direction, I can reject the null hypothesis. You say that the null hypothesis here is, if I believe my research hypothesis is as I increase x, y increases, my null is as I increase x, either y does nothing or y decreases. Or vice versa, if my null hypothesis is as I increase x, y decreases, then I'm hypothesizing a negative coefficient for beta, then my null is either 0 or positive. It's the opposite. If you have a strong theoretical reason to believe that you have only a one-directional effect, that your effect is definitely either positive or negative and never the other one, you can state that stronger research hypothesis, and it becomes a little easier to reject your null, because your null is sort of captured by more stuff. It's beta equals 0 or negative, or beta equals 0 or positive. And there, you're only looking for rejections in one direction. So now, if I'm saying my beta is somewhere positive, right, I'm going to reject my null. Sorry, back up. If my beta is either, if I'm assuming my beta is positive, my research hypothesis, my null is 0 or negative. I can reject the null then if the beta is sufficiently positive. If it's sufficiently away from the 0 or negative numbers, then I can reject the null that it's 0 or negative. And therefore I have support for my research hypothesis that it's positive. I made a little mess of that, so I'm going to repeat that again. If my research hypothesis is a positive beta, my null then is 0 or negative for beta. I don't then want to look for to see how far away my beta hat is in either direction, because my null is, it could be negative. So I'm looking only in the positive direction. So the further my beta hat is away in the positive direction, the more likely I can reject my null hypothesis. Because I'm looking only in one direction, we call it a one-tailed test. And we look to see if our test statistic, that we'll see in a second, if that is significantly different from 0 only in one direction. Because we're looking only in one direction, we put all of our 5% probability in that direction, and that means we end up having a lower value for a critical statistic of the 1.6 something instead of 1.96. 1.65 instead of 1.96. And so it's a little different. It's a little easier to reject our null hypothesis, But to use a one-tailed test, we must have a good, strong theoretical reason for why we're only looking for deviations from 0 in one direction and not both directions. Okay, so let's look at some more concrete pictures here. Here's a null hypothesis in a simple normal two-tailed test, which is the norm here. If we don't have a strong theoretical reason for a one-tailed test, we use a two-tailed test. In practice, the one-tailed test is the same as a two-tailed test at 90% confidence. Right? So if we don't have a really strong, believable reason to use a one-tailed test, we're effectively dropping our confidence down to 90% from 95%, which usually isn't looked upon well. So you want to have a really strong reason to use a one-tailed test. And if you don't, use a two-tailed test. Okay, so the null hypothesis on a two-tailed test is that beta equals 0. What does that tell us about the impact of x and y? Well, if this is beta equals 0, there's no effect of x and y. This, however, this line over here is our estimated effect. So we're trying to see if the estimated effect is significantly different from the null of 0 over here. How do we do that? Well, it turns out it's really easy compared to everything we've done before. You take your estimated coefficient, beta hat, you subtract the 0 null, which is just beta hat, and you divide by the standard error on beta hat, which was the thing given to you in your table from your statistical software, right? This thing. So I'm dividing basically the coefficient over here by a standard error. That's it. So you can actually eyeball out of this stuff. This is 0.0031 or 0.0007. That's greater than 2 when you divide this by this, so it's significant. You're done. So it's much easier in a lot of senses than what we did before once you've calculated a coefficient and a standard error. This is a t distribution. So again, if it's under 100 data points, you can use the t distribution. If it's over 100, you can use a normal distribution. The degrees of freedom that you look for on a table is the number of data points n minus the number of parameters. So before you had a single, you're looking for a single, you're measuring a single coefficient, and the number of parameters was 1 effectively. So you had n minus 1 degrees of freedom. Now you have n minus number of coefficients degrees of freedom. We have alpha and beta in this simple bivariate regression, so we have n minus 2 degrees of freedom. If we had if we had x1, x2, x3, and x4, we'd have 4 plus the constant, so 5 coefficients, so it'd be n minus 5 degrees of freedom. That'll come up in the next lecture. So now I compare. Well, here we have our value divided by the value of the standard error, which is, wait, I wonder when the numbers are different from before. Anyway, which is this. Oh, sorry, I used different rounding over here. So this divided by this gives you this. 4.55. We look at a table. We have 10 data points and two parameters, so it's 8 degrees of freedom. We look at the 0.05 level, and it's 2.3 is the critical value. 4.55 is greater than 2.3, so we can reject the null hypothesis at a 95% confidence level. In fact, we can do that at a 99% confidence level, since its critical value for 8 degrees of freedom is 2.9, and 4.6 is greater than 2.9. So we can reject the null hypothesis that there's no relationship between GPA and SATs at the 99% confidence level. And we can say, in fact, that there is a statistically significant relationship between SAT scores and GPA. Okay. So let's do another example here. Here's a theory that when the president is more popular, more people say that they are members of the president's party. Our data on this come from quarterly Gallup surveys in which you have average presidential approval and the percent of the respondents who say they're members of a particular party. And this is from 1960 to 96. So what are our variables? Our independent variable here is approval. We're trying to see the approval rating and how the approval rating, presidential approval rating, affects a dependent variable of the percentage of people who say they're members of the president's party. So self-reported partisanship, if it matches the party of the president. We again assume a linear relationship. So y equals alpha plus beta x. Here y is the percentage of people self-identifying with the president's party. And x is the percentage of people, as the percentage approval rating of that president. Here are our data. partisanship and approval rating split by party. Okay, and we can run an O.L.S model. To run this, you're just plugging into the earlier equation you saw for beta hat and alpha hat. You get a constant of about 37, and you get an approval rating of 0.255. Sorry, an approval coefficient of 0.255. So the first thing I want to ask is, does presidential approval have a statistically significant effect on partisanship? So all we're going to do is divide this coefficient by the standard error. We're going to get about 3. We have 142 degrees of freedom because we have 144 data points and 2 coefficients, 2 parameters. So we use a normal distribution, effect close enough at least, 1.98 here, close to 1.96. And we see it's in fact greater than that, so we can reject the null hypothesis that there's no relationship between presidential approval and self-identified partisanship at the 95% confidence level. Okay, so that's what we did before. Now I want to close this pretty long module out by talking about what more our model brings to the table than we had before when we just looked at bivariate correlations between x and y. Part of what it brings to the table we'll get to in the next lecture when we discuss more than one independent variable. This kind of method allows us to incorporate more independent variables than we could easily do just using the simple bivariate correlations, although there are variants of that as well. What we can also do out of this method, this O.L.S method, is get predictions to try to understand the size of our effects. Before, if the correlation was high, so it was like close to 1 or -1, we said there's a strong correlation. But we didn't really get actual numerical sizes of the effects, right? What does changing x do to y quantitatively? The O.L.S regression lets us do that because it produces a model and estimates a model of how x changes y. So we're going to start with 2 values of interest. So George H.W. Bush, so the first George Bush, President Bush, had a high point in his approval of 80% and a low point of 35%. That's a big swing. To figure out what predicted levels of partisanship we should have from these data, what we do is we take this equation here, this y equals alpha plus beta x. We use our estimated values of alpha and beta, and we plug in our x's. We plug in the x we care about for a prediction. So first we'll plug in 80%. And remember here, you want to plug it in the same units you had before. We used percentages before, so we want to keep it percentages now. We don't want to suddenly switch to 0.8. So you have 80 here. So you look at this equation down here. You have 80 over here. You have 0.255 as our estimated value of beta. So it's 80 times 0.255 plus our estimate on the constant, and we get about 57. So at the high point of first President Bush's approval, we would have expected partisanship around 57% attached to the president's party, Republican in this case. In the second case, at the low point of approval was 35%, so we do the same prediction, but now we plug in 35%, and we get 45.5% partisanship. So now we have a swing of about 11.5% in partisanship between the low and the highest levels of approval. There's uncertainty on these predictions, it's true, but it's important to know, on average, we're now getting an estimated size of the effect of approval using realistic approval numbers. The entire range of approval during President Bush's time in office would have shifted partisanship associated with his party 11.5%, which is substantial. Substantial degree of predicted partisanship shift. We can do the same thing with Reagan. Reagan had a little higher lowest approval and a significantly lower highest approval. Plug the same things in again, and I don't know why I have 35 here. They should both be 64 and 38, sorry. And you get 53% and 46.3%. So what we're seeing here is a much lower shift in partisanship corresponding to a lower overall range in approval ratings. So again, what it does, these predicted values get us a sense of how much the dependent variable changes with realistic changes in the independent variable. And we can do that for any value of x. The nice thing about our model is we can interpolate or extrapolate potentially. If we have values of an x that we don't see in the data, we can still plug them into our linear model, our line, and predict what we would have expected as a dependent variable associated with that particular value of x we plugged in. So if we didn't have any situation in which the approval rating was 50%, but we really were interested in 50% approval, we could plug in 50 and get a number, and that would be our prediction for partisanship given 50% approval. So we look, and this is back from before again in this slide. There is error. We can see there's a difference in partisanship based on approval between the different presidents. Okay, so just skip that. So just to conclude this section, what did that model do? It draws a straight line through the points. None of these actual observed points fall on that line, right, in general. We are not, in general, going to get lucky and have a situation in which we have the points in our data falling directly on a regression line. That's okay. We're trying to find the best fit line that minimizes the sum of squared errors of our data away from the line. Because our data don't exactly fit the line, our model is not going to perfectly predict values of the dependent variable, even though it might get close in certain cases. But it can do two things. It can tell us if our independent variable is affecting the dependent variable, and it can give us an improved prediction of our dependent variable from our independent variable, where it's improved relative to our first prediction, which you might remember was the mean of the dependent variable. Our first prediction was the mean of the dependent variable, just y bar. Now we've added another independent variable and increased the level of our predictive accuracy. This is really not much different than from what a lot of people in data science effectively do, is figure out what variables most increase the accuracy and prediction on a dependent variable. So we get the best model of prediction based on which variables do the best job in prediction and most contribute to our ability to predict. And that's what we're starting to do here. And we'll do more of that in the next lecture, but we're going to take a step back now and try to talk more about, for the next few modules, what exactly O.L.S is, what its assumptions entail, and so on.